False. A is diagonalizable if and only if A is equal to PD P inverse for some diagonal matrix D and invertible matrix P. True. That is the definition of diagonalizable. Okay. If D is the matrix 2, 0, 0, 3, how do you find D to the fifth? Yeah. It would just be 2 to the fifth, 0, 0, 3 to the fifth.
You could raise 0 to the power, but still.
Yeah. And true or false, an n by n matrix with n distinct eigenvalues is diagonalizable. True. All right, let's look at the notes from the 5-3 reading. Okay, so a diagonal matrix, the definition of a diagonal matrix is a matrix that has zeros everywhere except on the main diagonal. A square matrix A is diagonalizable if you can write it as PD P inverse, where D is diagonal and P is some invertible matrix. All right, so here's an important theorem. An n by n matrix is diagonalizable if and only if A has n linearly independent eigenvectors. So those n linearly independent eigenvectors make up the columns of P, and the corresponding eigenvalues of A make up the diagonal entries of D. So this is how you can diagonalize a matrix. You find its eigenvalues and its corresponding eigenvectors, and that's how you build your D and your P. So if an n by n matrix has n distinct eigenvalues, then it definitely has n linearly independent eigenvectors. So it will be diagonalizable. And here are the steps to diagonalize a matrix. You have to find its eigenvalues, find the corresponding eigenvectors to each eigenvalue, construct P using the eigenvectors as the columns, and D with the diagonal entries as the eigenvalues in the same order, right? So make sure the eigenvalues and eigenvectors correspond. Yes?
So we say we're finding
the basis for the eigenspace. Yep. Yep. Perfect.
Eigenspace is the null space too.
It's the null space of A minus lambda I. Yes. Oops. Okay. So the whole point of diagonalization is that it makes a lot of computations easier. I'm sure you'll see diagonalization used to simplify computations in several upcoming courses that you're going to take. One such computation that is easier is raising a matrix to a power. Because if D is a diagonal matrix, raising D to some power k means you can just raise the diagonal entries to the k. Way easier than doing D times D times D times D k times, because that's a lot of computations. And if A is diagonalizable, then to raise A to the k, you can just do A to the k is equal to P times D to the k times P inverse. So you only really have to raise the D to the k, and that's easy. So it's one computation that's much simplified by using a diagonalization. Okay, then we have one last theorem. The dimension of the eigenspace for each eigenvalue, so that's the number of vectors in the basis for the eigenspace, is always going to be less than or equal to the multiplicity of the eigenvalue. Right? So if you get an eigenvalue like lambda equals 2 with multiplicity 2, that means the dimension of that eigenspace will always be 2 or less. And a matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspaces is n. And if A is diagonalizable, then the collection of all bases of the eigenspaces of A forms an eigenvector basis of Rn. So that is, if I was going to say this shorthand, the columns you use to form P will be linearly independent and span Rn. The columns you use to form P will be a basis for Rn. Okay, so let's do some examples with diagonalization. So I've already diagonalized this matrix A here. So I've rewritten A as P, an invertible matrix P, times a diagonal matrix D times P inverse. So all the work of breaking it down into PD, P inverse has already been done. All right, so what are the eigenvalues of A? Those are the eigenvectors. The eigenvectors are the columns of P. The eigenvalues are the values on the diagonal matrix. So my eigenvalues are lambda equals 3 and lambda equals 6 with multiplicity 2. How do you find P? So first you find the eigenvalues using the determinant of A minus lambda I equals 0, right? And then you want to find the eigenvector that corresponds to that eigenvalue. We did this last class when you packed up and said, I'm done with this. Then you find the eigenvector, and that's what you put in P. Yeah. So P, the columns of P are the eigenvectors that correspond to the eigenvalues in D. Okay, so my basis for the eigenspace that corresponds to lambda equals 3. So lambda equals 3 is in the first column of D. So the first column of P is an eigenvector. It's one eigenvector from the eigenspace. Okay, so -1, oops, sorry, 1, -3, -1. So that's my basis for the eigenspace for lambda equals 3. And then my basis for lambda equals 6. So 6 shows up in columns 2 and 3 of the diagonalized matrix. So columns 2 and 3 of P are two linearly independent eigenvectors that correspond to lambda equals 6, which means that they form a basis. So those two vectors, 0, 1, 1, and 2, -1, 0, make a basis for the eigenspace for lambda equals 6. All right, if I want to evaluate a to the fourth, so I want to do it two ways. The first way is the long way, a times a times a times a. I have to write this out. 7, -3, -1, 2, 0, -2, -2, 6, 8. Times itself 4 times, and I could have my calculator do it, but it actually takes a lot of computing power. Even if you're having a calculator or computer do it for you, that's a lot of computations, so it would take a pretty good amount of time. Right, but if I wanted to do like a to the 100th, right, this would take a long time. Okay. Or if A were a larger matrix, imagine A is a 80 by 80 matrix. You're dealing with some situation, you have 80 variables, right? So, and you have to raise it to the 100th. That would take, you could have a computer do it, but it would take a lot of computing power and time. So you do end up getting, I don't even remember what you get. It's like, it starts out with 1701, -1215, -405. I'm not going to finish it. But to evaluate a to the fourth using PDP inverse, because I already have it diagonalized, right? I just have to raise d to the fourth. So it's going to be P, which was 1, -3, -1, 0, 1, 1, 2, -1, 0. That's my P. D to the fourth is just take each non-zero entry in D and raise it to the fourth. Times P inverse. And now you just have to multiply 3 matrices together. And one of them has a lot of zeros in it, so it's going to save you some computation there too. And again, I'm not going to do it out. But whether you're doing it by hand or having a computer do it, you're going to save time, right? Whether it's minutes by doing it by hand or nanoseconds, when you're writing a computer program, you know, little bits of time matter, right? Because they accumulate. Yes. All right. That's it. Start your activities. I'm going to suggest. I'm giving you a take-home quiz today, but I'm not going to see you again until Monday, right? And Monday is our review, and Wednesday is our next test. So I'm going to suggest that you work efficiently through the activities. Get your quiz when you're done. Work on your hand your quiz in before you leave today, if you can. If you want to take it home and think about it more, that's totally fine. I'm just going to suggest handing it in today so that you can get it back the day we review and have it to study for the test. If that makes sense. You don't have to. It'll be due Monday if you want to take it home and think about it. Yeah, I guess you can do that. You can you can do the quiz first, and if you don't finish it, if you don't finish the activities, you'll just be responsible for them before Monday.